Hello, and welcome to this sixth of 6 films about the kinetic theory. Yes, it is the last one, and the good news is there's no new material to cover here. This really is just supposed to be a review of the things that we've done, so it's a few practice questions on some of the key points in the topic. Okay, so starting with what is supposed to be a fairly simple question. Most people would probably get this one right, but it just touches on an interesting point which a lot of textbooks don't bother to mention. Increasing forces of attraction, well, we'd say that the gas has the weakest forces of attraction because the particles can move around completely freely. In a liquid they can move around, but they're fixed together, so the forces must be stronger than in a gas, but they must be weaker than in a solid where the particles are in fixed positions. They can't move around at all, they just vibrate on the spot. Bear in mind that particles will always be moving until we get to 0 Kelvin, and that's a temperature we can't achieve in this universe. Okay, so anyway, the point that this touches upon is the fact that although this is a correct answer in a test, you could actually argue that the forces are the same in all cases. It's just that as the kinetic energy of the particles changes, they notice those forces less and less. Okay, so this is actually true as well, but you'd need to explain this in a bit more detail in a test. So I would be definitely going for the first answer because it's simpler and it requires less explanation, although this one is true, and the reason I bring it up again is just because a lot of textbooks don't bother to mention it. They just gloss over that fact. Okay, moving on, sketch the relationship. As soon as you see these words, sketch the relationship, in a question, what you should be thinking is, I'm being asked to draw a graph here. Okay, so what have I got to draw a graph of? Well, pressure and volume. And to do that at constant temperature, so we're keeping the temperature the same, in other words, we're showing the effect of pressure on volume, or the effect of volume on pressure, without any other factors coming into play, so we're making it a fair test. So I put pressure over here and volume over there. Very large volume, so if I pull the plunger out of a syringe, I drop the pressure inside that syringe. If I get to an infinitely big volume, then I suppose the pressure will approach 0, but it will never reach 0 because the particles will eventually collide with the walls of the box. And then at very low volumes, so that is when I push the plunger of the syringe right in, the pressure starts to increase. Okay, or it doesn't start to increase, but it gets high. Okay, and what you ought to remember, I suppose, is that the relationship between these two things is an inverse relationship. Okay, pressure is proportional to 1 over V. Okay, so the curve will be that shape. An alternative here that you've got is to actually plot pressure against 1 over volume and show that's a straight line, because this is the same thing as saying pressure proportional to 1 over volume. Okay, so that's what we're doing there. Sketch the relationship, sketch some graphs to show that you remember what the relationships between quantities are for gases. Okay, this one here, it might not look like it's about the same thing as the last one, but it kind of is related. Okay, because we're changing the temperature and we're seeing what effect that has on the pressure. So we need to remember that pressure is proportional to temperature. If we'd been asked to sketch that, we could put pressure up here and temperature there and draw a straight line. Okay, if I double the temperature, I double the amount of energy that particles have, so they're going to hit the walls of the box twice as hard, and the pressures are going to double. Okay, I suppose what this question is trying to do is trying to trick you a little bit, because it's saying, oh look, the pressure looks like, the temperature looks like it's doubled. And if you think that, then you've forgotten that you've got to have the temperature in Kelvin. Okay, so to convert degrees centigrade into Kelvin, we add 273.15. And that's not a number that you have to remember, it's on the data sheet, okay? But you do have to remember that you have to add this to the degrees centigrade and not take it away. So this isn't a doubling of temperature, but an increase from 293.15 up to 313.15. Unfortunately, I don't have my calculator with me, but basically that's an increase by a factor of 313.15 over 293.15, and I don't know exactly what that is in my head, but it's about 20 out of 300, so about a 15th. So this is about, the new pressure is about 1 1/15 as much as the old one. Okay, not exactly, but you do that on a calculator in the test. Okay, so that question is all about remembering two things: the relationship between pressure and temperature, and the fact that we have to have temperatures in Kelvin when we're looking at these things. Okay, next one, true or false. This one is a deliberately vague question because it's trying to raise a number of points. Okay, all the particles in the gas at 200 Kelvin are moving faster than those in another gas at 150 Kelvin. So I suppose we probably ought to be thinking of a Boltzmann distribution here. Here is the line at 150 degrees. No particles have no energy. Okay, this is something that we kind of need to remember. It's the fact that particles will always be moving until we get down to 0 Kelvin, but that's a absolute zero. That's a theoretical temperature. It can't exist in our universe. Okay, and at 200 Kelvin, so again, no particles have no energy, but the most popular energy has gone up, and the high energies become more popular. Okay, so if energy is down here, kinetic energy more specifically, okay, then the percentage of particles with those energies is up there. Okay, now let's just label these. That's the 200 Kelvin, and that's the 150 Kelvin. Okay. Now the question we've maybe not noticed is that this isn't asking about the kinetic energy. It's asking about which particles are moving faster. So in a moment we're going to just remember that kinetic energy is equal to half mv squared. But before we do, let's look at the graph and say, have all the particles in this gas got higher speeds than that one? Or have they got higher energies to start with? Well, yeah, some of them do, right? And there's more particles with higher energies than there are here. But if I highlight maybe this part of the graph at the higher temperature and this part of the graph at the lower temperature, you can see that there are particles in the lower temperature that have higher energy than particles in the higher temperature. So this word is not true. It makes the thing false. Okay. On average, the particles in a gas at 200 Kelvin do have higher energy, but not all of them do. Okay, and now moving on to this bit, moving faster. This makes the question trickier still, because it sounds as if we've got two gases, one gas and another gas. Okay, now if they were the same gas, then all the particles would have the same mass, and certainly they would be moving faster on average as the temperature went up. But because we don't know if these two gases are the same, we don't know what mass the two particles have. Okay, so although the ones at 200 Kelvin have a higher kinetic energy, that could be just because their mass is so much bigger. Okay, so if the other ones had if the ones at 150 Kelvin had a very, very small mass, they'd need a very high speed to make up for that. Okay, and so they could be moving faster than the ones at 200 Kelvin on average. Right, so this is actually quite a tricky question, but it ends up being false. Okay, but lots of things to take in there. All right, might be worth watching that one again. Anyway, what happens to the temperature of a liquid as it evaporates? Okay, this might not be obvious, okay, but it's a good idea to draw a Boltzmann distribution for this as well. So here we've got no particles with no energy. We're going to mark on this graph some energy that particles need in order to evaporate, and we can show on our graph what particles have enough energy to evaporate. That's the area under this curve, okay? That is the total number of particles that have enough energy to evaporate. Again, energy is here, and percentage of particles is up there. So this is the total number of particles that can evaporate, and we can see that although most of them don't have that energy, and in fact on average they don't have that energy, some do, and so some will evaporate. On to this specific question, what happens to the temperature of a liquid as it evaporates? Well, remember here, this is getting you to think about the fact that the temperature is related to the average kinetic energy. Okay, and if I take out these high energy particles, okay, then my sample of gas will have fewer high energy particles, and so its average kinetic energy will fall, and that means that the temperature of the liquid will fall. This is really important to your body, because every time you sweat, the high energy particles, the high energy liquid particles that you've released from your body, well, I mean, you've released particles of all energies, but the ones with high energies, they'll evaporate and they'll leave behind lower energy ones. So the sweat that is on the surface of your skin will gradually drop in temperature and cool your body down. Okay, so this question, I suppose, is getting you to think of a number of things. What happens when a liquid evaporates? Which particles escape? And also the fact that temperature is related to average kinetic energy, and getting you to think about Boltzmann distributions again. And this is the last question that we're going to look at here, because we're getting onto vapor pressures now, and this was the last thing we looked at in the topic. We're comparing two liquids here. We're comparing ethanol and water. We're being told that ethanol has a boiling point of 78 degrees. Remember, boiling point means this is the temperature at which the vapor pressure of the liquid equals the external pressure. Okay, we should know that water boils at 100 degrees centigrade at atmospheric pressure. Okay, here at sea level. Okay, so water has the higher boiling point. Okay, so that means I have to raise water to a higher temperature before its vapor pressure will equal this. Okay, so in other words, at any particular temperature, right, because ethanol is more able to evaporate, or in other words, the forces between its particles are weaker and there's more vapor above the liquid at any set temperature, the vapor pressure of ethanol would be lower at the same temperature as water. It boils more easily, it evaporates more easily, and therefore forms more vapor at any particular temperature. Okay, so this question is getting you to think about what boiling points were, what they've got to do with pressures, okay, and comparing two liquids with different boiling points to see what vapor pressures they have. The vapor pressure of two liquids will always depend on their temperature, but if they're at the same temperature, then the liquid with the lowest boiling point will have a higher vapor pressure at any temperature you choose to mention. Okay, so that's the review of the topic. Hopefully it all makes sense. There's undoubtedly some difficult things in that topic and some quite complex ideas to get your head round. Okay, can I suggest that you have a look over your notes again and check that you understand them. Okay, if there's things in there that you don't understand, then revising for your test is going to be extremely hard.